The maximum number of conductors permitted in a single raceway is determined by the raceway size and the type of conductors used. Table 310.15b2 provides information on the maximum number of conductors for various raceway sizes and conductor types. For metal raceways, the maximum number of conductors permitted is determined by the raceway size and the number of current carrying conductors. The formula for calculating the maximum number of conductors is maximum conductors equals raceway area divided by conductor area divided by 1.25, where raceway area is the area of the raceway in square inches, conductor area is the area of each conductor in square inches, and 1.25 is a safety factor. For example, for a 1-inch trade-size conduit with an area of 1.4 square inches and using THHN conductors with an area of 0.26 square inches, the maximum number of conductors permitted is maximum conductors equals 1.4 divided by 0.26 divided by 1.25, which equals 33.28. Truncating to the nearest whole number, the maximum number of conductors permitted is 33. However, there is a special exception for metal raceways with an area of 1 square inch or less. For these raceways, the maximum number of conductors permitted is 45, regardless of the conductor type. This is because raceways with a smaller cross-sectional area have less space for heat dissipation. Let's delve deeper into the National Electrical Code, or NEC, specifically focusing on conductor fill in metal raceways. Understanding these regulations is crucial for electrical safety and ensuring installations meet code requirements. The NEC provides guidelines for the maximum number of conductors allowed in a raceway to prevent overheating and potential fire hazards. We will be referencing NEC section 310.15b2 throughout this discussion. This section is vital for determining the allowable ampacity of conductors in a raceway. Ampacity refers to the current carrying capacity of a conductor, and is essential to ensure that the conductors are not overloaded. Overloading can lead to excessive heat buildup, insulation damage, and ultimately electrical failures. Firstly, the number of conductors permitted in a raceway is not arbitrary. It's based on calculations considering several factors. These factors include the size of the raceway, the size of the conductors, the type of insulation, and the ambient temperature. The NEC provides tables and formulas to assist in determining the appropriate conductor fill for different types of raceways. Secondly, the formula mentioned earlier, maximum conductors equals raceway area divided by conductor area divided by 1.25, is a simplified representation of the calculations involved. The raceway area refers to the internal cross-sectional area of the raceway, which is typically provided by the raceway manufacturer. The conductor area is the cross-sectional area of each conductor, including its insulation. This information can be found in the NEC tables or conductor specifications. The 1.25 factor is an adjustment factor that accounts for the deteriorating of conductor ampacity when multiple current-carrying conductors are present in a raceway. This deteriorating is necessary because multiple conductors generate more heat, which reduces their ability to dissipate heat effectively. Now let's consider the example of a 1-inch trade-size conduit. A 1-inch conduit has an approximate internal area of 1.4 square inches. If we are using THHN conductors, which have a cross-sectional area of approximately 0.26 square inches, we can calculate the maximum number of conductors allowed. Plugging these values into the formula, we get maximum conductors equals 1.4 divided by 0.26 divided by 1.25, which equals approximately 33.28. As we cannot have a fraction of a conductor, we round down to the nearest whole number, which is 33. Therefore, the maximum number of THHN conductors allowed in a 1-inch conduit, according to this calculation, is 33. However, it's important to note the exception for metal raceways with an area of 1 square inch or less. In these cases, the NEC permits a maximum of 45 conductors, regardless of the conductor type. This exception is based on the understanding that smaller raceways have limited space for heat dissipation. To compensate for this, the NEC allows a higher conductor fill, but it also requires careful consideration of conductor ampacity and temperature ratings. Let's discuss some additional factors that influence conductor fill calculations. One important consideration is the type of conductor insulation. Different insulation types have different temperature ratings which affect their ampacity. For example, THHN conductors are rated for higher temperatures than some other types of conductors, allowing them to carry more current. It's crucial to select conductors with appropriate insulation for the application and to factor their temperature ratings into the conductor fill calculations. Ambient temperature also plays a significant role in conductor ampacity. Higher ambient temperatures reduce the ability of conductors to dissipate heat, which lowers their ampacity. The NEC provides correction factors for ampacity based on ambient temperature. These correction factors must be applied to ensure that conductors are not overloaded in high-temperature environments. Another important consideration is the presence of other heat-generating equipment near the raceway. If a raceway is located near equipment that produces a significant amount of heat, such as transformers or lighting fixtures, the ampacity of the conductors in the raceway may need to be further dilated. The NEC provides guidelines for dilating conductors in these situations. In addition to the general rules for conductor fill, the NEC also includes specific requirements for certain types of installations. For example, there are special rules for underground installations, installations in wet locations, and installations in hazardous locations. These special requirements are designed to address the unique challenges and potential hazards associated with these types of installations. It's essential to consult the NEC for the specific requirements that apply to a particular installation. Furthermore, it is vital to understand the difference between current-carrying conductors and non-current-carrying conductors. The NEC defines a current-carrying conductor as a conductor that carries electrical current under normal operating conditions. Non-current-carrying conductors, such as equipment-grounding conductors, are not considered current-carrying conductors for the purpose of conductor fill calculations. However, it is still important to include non-current-carrying conductors when determining the overall size of the raceway. The equipment-grounding conductor provides a path for fault current to return to the source, which helps to protect against electrical shock and equipment damage. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device, such as a circuit breaker or fuse. In addition to the NEC requirements, local codes and regulations may also apply to electrical installations. It's important to check with the local authorities to ensure that all applicable codes and regulations are followed. Local codes may have additional requirements or restrictions that are not included in the NEC. Failure to comply with local codes can result in fines, delays, and even the rejection of the installation. To summarize, determining the maximum number of conductors permitted in a metal raceway requires careful consideration of several factors, including the size of the raceway, the size of the conductors, the type of insulation, the ambient temperature, and the presence of other heat-generating equipment. The NEC provides tables, formulas, and guidelines to assist in these calculations. It's essential to consult the NEC and any applicable local codes to ensure that all requirements are met. By following these guidelines, we can ensure that electrical installations are safe, reliable, and compliant with the applicable codes and regulations. Remember, electrical safety is paramount. If you are not comfortable working with electricity, it is always best to consult a qualified electrician. Working with electricity can be dangerous, and it's important to take all necessary precautions to protect yourself and others. Always to energize circuits before working on them and use appropriate personal protective equipment, such as gloves and safety glasses. In conclusion, understanding the NEC requirements for conductor fill and metal raceways is essential for electrical safety and compliance. By carefully considering the factors discussed and consulting the applicable codes and regulations, we can ensure that electrical installations are safe, reliable, and compliant. Also, remember that specific requirements may vary based on local regulations and the specific application. Always consult with a qualified electrician or electrical inspector for guidance on specific projects. The information provided here is intended for educational purposes and should not be considered a substitute for professional advice. Always follow the manufacturer's instructions for electrical equipment and materials. Use caution when working with electricity, and always prioritize safety. With a thorough understanding of the NEC and careful attention to detail, you can ensure that your electrical installations are safe and compliant. Always refer to the latest edition of the National Electrical Code for the most up-to-date information and requirements. The NEC is a living document that is updated regularly to reflect changes in technology and best practices. Staying current with the latest edition of the NEC is crucial for ensuring that your electrical installations meet the highest standards of safety and reliability. Always use properly rated tools and equipment when working with electricity. Using the wrong tools or equipment can be dangerous and can lead to electrical shock or equipment damage. Inspect your tools and equipment regularly to ensure that they are in good working condition. Replace any damaged or worn out tools or equipment immediately. Never work on electrical equipment while standing in water or on a wet surface. Water is a good conductor of electricity, and standing in water can increase your risk of electrical shock. Always wear rubber-soled shoes and work on a dry surface when working with electricity. Be aware of your surroundings when working with electricity. Avoid touching metal objects or surfaces while working on electrical equipment. Metal is a good conductor of electricity, and touching metal objects can increase your risk of electrical shock. Keep a safe distance from overhead power lines when working outdoors. Overhead power lines can carry thousands of volts of electricity, and coming into contact with them can be fatal. Always call before you dig to avoid damaging underground utilities, including electrical cables. Damaging underground electrical cables can be dangerous and can cause power outages. If you are unsure about any aspect of electrical work, consult with a qualified electrician. A qualified electrician has the knowledge and experience to perform electrical work safely and correctly. Attempting to perform electrical work without the proper training can be dangerous and can lead to electrical shock, fire, or equipment damage. Remember, electrical safety is everyone's responsibility. By following these safety tips, you can help to prevent electrical accidents and injuries. Always prioritize safety when working with electricity, and never take risks that could put yourself or others in danger. Proper planning is crucial for any electrical project. Before starting an electrical project, take the time to plan the project carefully. Consider the scope of the project, the materials needed, and the safety precautions that must be taken. Develop a detailed plan and follow it carefully. This will help to ensure that the project is completed safely and efficiently. Always obtain the necessary permits before starting an electrical project. Many jurisdictions require permits for electrical work. Obtaining the necessary permits ensures that the work is inspected and meets the applicable codes and regulations. Contact your local building department to determine the permit requirements in your area. Use the correct wiring methods for the application. The NEC specifies different wiring methods for different applications. Using the correct wiring method is essential for ensuring the safety and reliability of the electrical installation. Consult the NEC for the appropriate wiring method for your application. Make sure that all electrical connections are tight and secure. Loose or corroded connections can cause overheating, arcing, and electrical failures. Check all electrical connections regularly to ensure that they are tight and secure. Use the correct size of wire for the circuit. The size of the wire must be adequate to carry the load of the circuit. Using undersized wire can cause overheating, voltage drop, and electrical failures. Consult the NEC for the appropriate wire size for your circuit. Protect electrical wiring from physical damage. Electrical wiring should be protected from physical damage by using conduit, raceway, or other protective measures. Physical damage to electrical wiring can cause shorts, ground faults, and electrical fires. Install ground fault circuit interrupters, or GFCIs, in wet locations. GFCIs are designed to protect against electrical shock in wet locations such as bathrooms, kitchens, and outdoor areas. GFCIs detect ground faults and interrupt the flow of electricity, preventing electrical shock. Test GFCIs regularly to ensure that they are working properly. Install arc fault circuit interrupters, or ASIs, in bedrooms. ASIs are designed to protect against electrical fires caused by arcing faults. Arcing faults can occur when electrical wiring becomes damaged or loose, creating a spark that can ignite nearby combustible materials. Test the size regularly to ensure that they are working properly.